All right, we're back. This time we're going to talk about some special solutions to our evolution equations. Okay, so this is what we were doing last time, just setting up the problem, talking about the geometry of it, giving the energy decay for the free elastic flow and the length decay for the curved diffusion flow. And in establishing these equations, we should probably just write down that the boundary conditions, we call them BCs, are crucial for these equalities. So if you have a different boundary condition, so instead of the no flux, like let's just say that for some reason you wanted to say Ks equals 1 on the boundary, then the curved diffusion flow would no longer reduce length. You would destroy that property. So this is, it's another motivation for it. It's a fact. All right, so let's keep going. I don't want to use black anymore. We are going to talk today about special solutions. Basically, we want to think about some ideal situations for our problem and see if we can learn anything from thinking about those. Okay, so let's draw our setup again. And we've got these two parallel lines and we've got a curve that spans them. And let's make this curve, here's one special solution. Right? Why is that a special solution? Because if I write down what the curvature is of this curve, what do I get? Well, oh, sorry. I get 0. It's 0. And its derivative is 0, so that means that this horizontal line does not move under either flow. It's an equilibrium configuration. Okay, so you might think this is a bit like the ball in the bowl. Let me just briefly, so here's a bowl, and here's a ball. You might think it's like this. Okay, but that is a little bit wrong. Because, there's another line here, and there's another line here, and there's one here too. And in fact, we have a continuum of horizontal lines. And so there are many, many, many equilibria, and they're very close to each other. So it's a bit like, now my drawing skills may fail me, but this is a little bit like the situation where you might have some kind of trough. So imagine you have, this kind of configuration, like a bowl, but instead of being round on all the sides, it sort of continues off in one direction. And then you can place inside this bowl your little ball, okay, maybe place it in the middle there, and that will be stable as long as it's kind of perfectly flat. Be stable, not stable. It'll be in equilibrium as long as it's perfectly flat. But so would it be in equilibrium if the ball was there, or the ball was there, or the ball was there, or there. And these are like these lines here. And you can kind of imagine that if you disturb this ball, then it might roll forever. If there's no friction, it could roll forever. So you need some kind of other force, like friction or resistance of some kind, to slow it down. And really, that's the main difficulty with what we're trying to do here, is proving that you don't need it in this case. Okay, so I'm going to get rid of that because it's kind of ugly, but that's my drawing for you. Okay, so we call this a continuum of equilibria, or a manifold. Now, you don't need to worry too much about this word manifold, just think equilibrium, but I'll still use the word. So it's a manifold, one-dimensional, because there's only one degree of freedom of equilibria or horizontal lines. Let's call them equilibria. And I'll put in brackets horizontal lines. Okay. Now, it turns out to be the case that there are no other equilibria. There are no other steady state solutions in the case of the curved diffusion flow for CDF. However, for the free elastic flow, there do turn out to be many more, which I will describe shortly. Before I do that, let's think about some other simple shapes. Okay, so you've got straight lines, they're pretty simple, but in the flat plane, there are also some other simple shapes. So another one is that I can draw with the help of my technology here is a circle. Look at that circle, beautiful. So I'm going to write the word circle. Okay, so here's a circle. Now you might say, well, Glenn, so what? I mean, this does not satisfy your boundary conditions. And you're right, it doesn't satisfy my boundary conditions, but it's still important to think about. Now, on this circle, we've got curvature. Now, if you think about it, a circle bends the same all the time. And so basically what this is an example of is a curve where the derivative of the curvature is 0. And so that means that it doesn't do anything for curved diffusion flow. It's an equilibrium. And any circle with any center and any radius is an equilibrium. And the curvature itself is a constant, positive constant. In fact, it's just the reciprocal of the radius, but we don't need to know that. So what this means is that for this is an equilibrium for curved diffusion. But if you look back at the free elastic flow, like let's have a look back here, this first term would be 0 for a circle, but this second term will not be 0, and in fact it will be positive, and then there's a negative, and the normal points inside. So what it means is that this will expand, and as it expands, it just never stops. It just goes bigger, 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 bigger. Curvature gets smaller because it's a reciprocal of the radius, but it never stops. So we call this an expander. It's an expander for the free elastic flow. Okay. Now, this, even though this has Ks equals 0, so it would satisfy the boundary conditions, how can you satisfy the angle condition? Well, basically, difficult. You can, come out here and then you make a right angle there, and you can come out here and make a right angle here, but these lines are not parallel. So, I mean, if you have skew lines, then you could have a circle expanding out, again, like Jacob's ladder, but in our case, this can't happen. So we rule these solutions out. So there's a ruled out. We assume they don't happen. Okay, what's another type of special solution? Another kind of special solution is an elastica. And in fact, the most important kind of elastica for us in this situation is what's called the rectangular elastica. What I might do to give myself a little bit of space is just shrink these guys down. Look at that. Black magic. Okay, so Here we go. What is a rectangular elastic arc? Well, basically you need to draw these dotted lines. Vertical line here, horizontal here, horizontal here. And then I'm going to do my best. My drawing skills are not great, so please be kind. Okay, so they come up here. Oops, I should turn off the straight line mode. They come up here. They hit. Come on. They come up here. Too fast. They come up here and they hit this middle point and they become vertical very briefly. Just for a single moment, they're vertical. And then they flatten back out again. But I should try to make it so that it does it, so that it lines up here. Okay, so these satisfy the boundary conditions. They're 90 degrees. They have curvature derivative equals 0 only at these endpoints. And they are not flat lines. Now what you can do, this is a half period. What you can do is split up this intermediate section into many more periods. So you can have things that look like this, which are 2. So that's one whole period of this elastica. Or you can squish it up even more and you can have many, many periods of this curve. And in this way you can construct infinitely many free elastica that will be stationary solutions to the free elastic flow. So this is called rectangular elastica. It's an equilibrium for the free elastic flow. There are infinitely many. They're quantized at various energy levels, which I will... Because if you think about it, the total elastic energy is total bending. And as you add more periods, it bends more and more and more. So there is an energy quantization for these curves, but still they happen. So if you're talking about equilibria, there are a lot of them with elastica, but for curve diffusion, not as many. Okay, so these are the key ones that I want you to keep in mind. We do not rule out this, so this is an issue. These rectangular elastica have not been ruled out, and that makes the main difficulty for the free elastic flow. For the curve diffusion, we have a different difficulty, which I'll explain now. And this is not so much a special solution as it is some sort of nightmare. So let's say what is the nightmare? Okay. Well, to start with, we draw 2 arcs of a circle. So we draw one circular arc like this, and another circular arc like this. These are supposed to be circular arcs, so they have 0 derivative of curvature. And then in the transition layer between these 2 arcs, we don't know what happens. We could have some kind of curve like this, or it might be more complicated. If you can't see what I drew there, I drew this little S shape. Why did I draw an S shape? Because an S shape like this is half of what we call what I try to draw as a lemniscate of Bernoulli. And the lemniscate of Bernoulli is a special solution to, so let me write this down, lemniscate of Bernoulli. The lemniscate of Bernoulli shrinks under curve diffusion flow. So it shrinks, becomes smaller and smaller and smaller, and then disappears. And that's a pretty bad situation for us, because if you imagine in this configuration here, like let's just imagine for a second that this part in the middle is shrinking, then what exactly is going on is we have sort of an arc. Now, this is not a rigorous mathematical proof. This is not proved. It's just a nightmare. We have sort of a circular arc that comes up like this, and another circular arc that comes down like this, and then there's this complex transition layer. So that's really what I want, the message I want to get across here is complex transition. Okay. Okay, now why is this a problem? It looks nice, right? But it is a problem because on this arc, you basically have, say, curvature equals 1, and up here you have curvature equals -1, and that's discontinuous. You know, that is like the curvature going from positive to negative without anything in between. Maybe it smooths out, but maybe not, because you can place these shrinking guys here, and that might produce what we call a singularity. So, is this a singularity? Sort of a nightmare. Okay, I think I've spoken for long enough in this video. That's it for now. In the next one, I'm going to give you some real nightmares, some things that definitely do happen that are bad that we need to rule out. So this one is a possible issue. The rectangular elastica are real issues. And in the next one, I'll give you some more real issues. Anyway, that's it from me. Thanks for your attention, and I'll see you in the next one.